When you plug something in, you just expect it to work. But have you ever really thought about the journey that electricity takes? Especially from something like a battery or a solar panel. It's not born perfect. No, it's raw, it's messy. So today, we're going to explore the incredible art of electrical sculpting, how engineers take that dirty power and carve it onto the pristine energy our modern world depends on. And right here, this is the whole challenge in a nutshell. Over on the left, that's our masterpiece, a beautiful, smooth sine wave. That's the clean power we get from the grid. But on the right, well, that's our starting block of stone. It's the jagged, chunky square wave that a basic inverter spits out. The big question is, how do we get from that rough block to the finished statue? So what makes that square wave so ugly? Well, it all comes down to these things called harmonics. You can just think of them as electrical noise. They're all the unwanted frequencies, the rough edges and jagged bits on our signal. And our job as electrical sculptors is to find a way to chip all of those unwanted harmonics away until we're left with just the pure, clean signal we actually want. Looking at it this way really makes it clear. See that big, tall bar? That's our fundamental frequency, the 60 Hz signal. That's the part we want to keep. But all those other, smaller bars, the third harmonic, the fifth, and so on, those are the bad guys. That's the noise we've got to get rid of. All right, so you're the sculptor. Where do you even begin? Well, it turns out the very first tool you use is this incredibly clever and honestly super simple trick that gives you a massive payoff right from the start. It's called half-wave symmetry. All this means is you engineer the wave so that the negative part is a perfect flipped mirror image of the positive part. And just by doing that one thing, bam, you magically get rid of half of your problem. All the even-numbered harmonics, the second, fourth, sixth, they just vanish. Poof, gone. And don't underestimate how huge of a win this is. As MIT's David Peralt explains here, that second harmonic is a real pain to deal with because its frequency is so close to the one we want to keep. It's like trying to pull out a single weed that's growing right next to your prize-winning flower. By getting rid of it with a simple symmetry trick, we make the rest of the job so much easier. Okay, so we took a big sledgehammer to the problem and knocked out all the even harmonics. But we're still left with the odd ones, the third, the fifth, the seventh. For those, we need to pull out a more precise tool. We need a fine chisel. And that chisel is a technique called harmonic elimination. It's pretty amazing. Engineers can literally target one specific harmonic they want to kill, say the third. Then they do the math to figure out the exact precise moments to add these little notches into the wave. They add the notches, and just like that, the harmonic they targeted is gone. And check this out. This is how precise we're talking. To get rid of that annoying third harmonic, it turns out if you put the notches at exactly 30 degrees, the math works out perfectly so that the total energy from that harmonic over one cycle adds up to 0. It literally cancels itself out. It's pure mathematical sculpting. Of course, you can't get something for nothing, right? There's always a trade-off. Every notch you add means the electronic switches inside the inverter have to flip on and off more often, and every time they switch, a little bit of energy is lost as heat. So, the cleaner you make the wave, the less efficient the whole process becomes. You're trading purity for power. And basically, the rule of thumb is pretty simple. For every extra pulse or notch you're willing to add, you get to pick one more odd harmonic to eliminate. So, if you want to get rid of the third and the fifth, you're going to need 2 pulses. It's a direct one-for-one trade. So that's one way to do it, chipping away at a single block. But what if there was a totally different approach? What if, instead of starting with one imperfect block, you could take 2 imperfect blocks and combine them to create something nearly perfect? Well, that's the beautiful idea behind this next technique. This is called harmonic cancellation, and it's just a brilliant concept. You start with 2 separate inverters, and you have each one create the exact same simple, messy waveform. Then you take one of those waves and you just delay it. You shift it in time by a very specific calculated amount, and then you add them together. And this is where the magic happens. Let's say our enemy is the fifth harmonic. It turns out if you shift that second wave by just 36 degrees, its fifth harmonic actually gets shifted by 5 times that amount, which is 180 degrees. And what's a 180-degree shift? It means it's now the perfect opposite of the fifth harmonic in the first wave. So what happens when you add something to its perfect opposite? They completely annihilate each other.
The unwanted harmonics literally cancel themselves out of existence. And what you're left with is a combined wave that is so much cleaner and closer to that perfect sine wave we're after. It's just an incredibly elegant solution.
So, now we've got these two powerful paths to a pure signal, and each one comes with its own pros and cons. Harmonic elimination carves up one wave, but you lose energy in the process. Harmonic cancellation teams up two waves, which can be more efficient, but it means you need more hardware. It's this constant balancing act that engineers have to navigate every single day. Now, you might be thinking, okay, that's some really cool engineering theory, but this isn't just happening in a lab. This electrical sculpting is happening all around you, right now, inside the tech you rely on every single day. That solar inverter on your roof converting DC power into AC for your house? Yup, it's doing this. That battery backup, or UPS, that keeps your computer running when the power flickers, it's sculpting a perfect sine wave. Electric vehicles use these techniques for super precise motor control. Heck, even your computer's motherboard uses a version of this called interleaving to deliver rock-solid, stable power to your processor. It's everywhere. So these incredible techniques are the hidden artistry that powers our modern world, turning rough, chaotic electricity into finely tuned energy. It really makes you stop and wonder, right? As our technology demands power that's even more efficient, even more precise, what amazing new sculpting tools are engineers going to invent next?